During this course, we're going to learn and go through static reverse engineering, focusing on multiple targets and leverage them against both kernel drivers, userland targets, primarily Windows, but we will be seeing some macOS and Linux targets as well, and more. I'll kind of dive into that shortly as we go through the what to expect section. And then we'll also move on to actually looking at CPU and memory, tooling, everything about Windows, so the ABI, APIs, things like that. They're kind of bunched into day one, and day 2, 3, and 4 will expand on them. We'll actually reverse engineer live targets. We will reverse out structures, understand obfuscated targets, malware, targets that have vulnerabilities in them that we'll find as well, and kind of take it from there. So what to expect? As I kind of briefly mentioned, it's not just one target. This isn't a dedicated malware reversing course. This is for reverse engineering in general. So as part of this, we'll be targeting both malware and vulnerable software, and also just some interesting software in general. We'll be using some open source software, tools like Ghidra, but I may also pull out IDA or Binary Ninja here and there as well. Primarily Binary Ninja a lot, but you'll find that a lot of the usages of these tools are very similar. Typically, you just have a brief experience with all of them. Generally, you'll form a initial liking to perhaps one over the other, and then it's just a matter of getting familiar with the APIs and internals of the tool, because half the time each tool has very similar capabilities, especially if you're comfortable extending it via scripts and plugins, which just comes down to personal preference. And also during this course, we're not going to do any live debugging at all. It's going to be completely static. Now, some of the challenges and things like that do get easier if you were tying in dynamic analysis, such as, attaching a debugger to code and running it. But we're going to focus entirely on static for multiple reasons. One is you're not always going to have an environment where you can attach a debugger easily. Think of the case where you're trying to find a 0-day in the latest version of iOS on an iPhone or something, and you've unpacked the firmware for it, so you can load it up in, Ghidra or something, but you don't have a jailbroken iPhone running that latest version to be able to attach a debugger to it. That means you have to kind of do things statically, right? Additionally, the more you hone your static analysis skills, the better your debugging will be as well, because you'll be more comfortable understanding the disassembly and what you're actually looking at in the debugger as you step through the target. So this is a very important skill that mainly comes with practice. There's no real secret to it other than getting some helping hand knowledge with structures and things like that, but then it's just a lot of practice, which we'll be going through with some of the targets we've chosen as well. And the formats of the targets we'll be looking at, they're going to vary as well. They're not limited to just userland executables. We also look at kernel drivers, code that's obfuscated, and also I'll chuck in some Mac samples in there as well, although the majority of what we'll be looking at will be Windows code. To begin with, we're going to look at some of the initial theory, mainly around CPU and memory, because when you're reverse engineering, you're looking at binary data that's going to be loaded up into memory and executed by the CPU. So it is very hardware dependent. Looking at the disassembly of one processor might be completely different to another, especially if they're on different architectures. And while this course also mostly focuses on x86 and x64, we will look at some ARM examples later as well. Now, when it comes to the general operation of a CPU, so what typically happens is there's certain registers in CPUs, and one of the registers corresponds to what we can generally refer to as a program counter or instruction pointer register, and that's just a name for the register that contains the address in memory of the instruction to execute. So that could be virtual memory or physical memory, which we'll look into memory shortly. But in general, it's going to be some memory address, and the instruction pointer is going to point to it. The CPU is going to retrieve or fetch the data located in that memory address, and it's going to interpret the binary data there as a instruction. So it's going to attempt to decode that binary into an instruction. So in this case, we can see the CPU's fetching from some offset in RAM that contains the address, contains the data 0xFFE0. And that's going to get decoded into the jump RAX command, and the CPU will then execute that instruction. That's kind of the general flow of how a CPU operates. Of course, there's interrupts and things like that, but generally, when a CPU has an instruction pointer pointed somewhere, it's just going to continue fetching from memory and executing until certain things happen. Now, the decoding process, where the binary data is actually turned into an instruction, that is generally in the manuals of the CPU as well. So, in x86 Intel's case, if I go on the internet and download the software development manual for Intel, there'll be a table or a list somewhere that actually contains the decodings for the instructions. So for the jump instruction, it'll tell you which bytes correspond to the jump instruction, and then which binary bits determine which register or location it's jumping to, and things like that. Those details aren't really necessary to understand unless you're writing a decoder yourself, where you want to emulate a CPU perhaps by reading in binary data as instructions of a specific model. But it's good to understand how the CPU does these things. Especially since sometimes CPU code or code that's actually instructions may not be immediately recognized as such in tools, but we'll tackle that later. Additionally, there's some other certain behaviors between different processors to keep in mind. Some processors like x86 Intel are little endian, which means the least significant byte is first, which means if you see something like 0xFFE0, generally the CPU then will kind of reverse it so that it reads from the least significant byte in the data first, or bit in the data first. So the CPU will actually consume it as 0xE0 first, followed by 0xFF. While other systems are big endian, which means they'll actually store the most significant value first, which means a big endian CPU would read it as 0xFF first and then 0xE0. Again, this is kind of just like some of the key things that pop up when you look at different processors and how they consume data. The next major component to understand is memory, specifically the memory management unit, or MMU. So at the bottom, highlighted in yellow, I've got a virtual memory address, and typically the environments we execute code in use virtual memory, which can be toggled on and off many CPUs by configuring certain system registers in the CPU. So typically the system will boot up with no virtual memory at all. You'll just be interacting with the direct physical memory, and then the operating system or the bootloader will transition into virtual memory mode. And there's a few benefits to working in virtual memory mode. But to first clarify what that is, when you're running like Windows or Linux or Mac, when a process refers to a specific or a specific address in memory or in RAM, typically that's going to be a virtual address. What that means is that that virtual address is going to be broken down into components and looked up in a page table. And then there's going to be a specific entry corresponding to each address. And that entry is going to point to the actual physical memory in RAM where your data exists. So say, there's a process that wants to read from address 0x 20,000. Or I guess in this case, 0x1222. When my process goes to read from that address, it doesn't look up in actual RAM that 0x1222 address. Since virtual memory is enabled, the CPU will detect that I'm trying to access this address, and the CPU will translate it into physical memory. And the way that happens on x86 is that there's a physical address stored in the CR3 register, which is a system register that cannot be modified by userland processors. Typically, the kernel will intercept modifications to it to protect it. And that CR3 register will contain the physical address of where the page tables live in memory. And the page tables, it's a specific structure, it's a hierarchy, and the virtual address you provide, like 0x1222, gets broken down or sliced up into bits and used as indexes into different offsets of that table, of the page table. And eventually it resolves if it's mapped to a page table entry. And that page table entry contains the location in physical memory that contains the data for that virtual address. Which means that if I go to access virtual address 0x1222, that may actually translate to physical address 14119 as an example. And then the CPU will fetch the contents from that actual 1419 address from RAM. And the reason why we have this translation layer is so multiple processes can access the same virtual memory address, right? Process 1 and process 2 can both access virtual memory 1222. But since both processes will have different CR3 registers, the actual physical memory that they access can be different. In process 1, that virtual address can translate to 1419. But maybe in process 2, the exact same virtual address translates to 2340 or something completely different. It's a way of providing isolation of memory between processes. That said, there's nothing stopping virtual memory from being mapped to the same physical memory address and things like that. The kernel and the operating systems responsible for the mappings. And if you're in kernel land, you can always create your own mappings as well so that you can access any physical memory by setting any virtual address with a page table entry to that physical address. Consequently, this is how memory can be shared between different processes as well. You can have the same or different virtual addresses in two separate processes, and you can actually translate them to either the same address or different addresses. So if I map in the same physical address to two separate processes, I can say in process 1, the virtual address 0x8880 is going to equal to the physical address AB00. And in process 2, the virtual address EF00, which is a different virtual address than in process 1, I'm going to map that to the exact same physical address in process 1, which was AB00. That means whenever proc1 accesses 8880 and whenever proc2 accesses EF00, they're actually going to be accessing the same underlying physical memory, which means there's a shared memory mapping between the two processes, and they can communicate between each other through this shared memory address that's mapped into both of them. So that's how shared memory works. It's just the same underlying physical memory mapped into two separate processes, page tables, so that they have some virtual address to refer to that actually corresponds to the same physical address. Likewise, this happens a lot for performance reasons as well, or memory usage reasons, where a shared memory is read-only. Think of something like NTDLL on Windows. It's a DLL that's loaded into every single process space. Now, if we actually allocated physical memory for every single process to contain NTDLL in memory for that process, that would be a whole heap of wasted memory. So what happens instead is NTDLL gets mapped into memory precisely like one time into physical memory. And then for every new process that's launched, it'll have a virtual memory mapping to that one physical memory address containing NTDLL. And that's how NTDLL is accessible or loaded into every process without needing to allocate memory for NTDLL in every single process. You just allocate it once and make sure that every process has a virtual memory mapping to that one physical mapping of NTDLL. Additionally, page tables contain metadata as well, not just the translation. So for any translated address, there's a set of bits corresponding to metadata that can make the address read-only, it can make it read-write, it can make it non-executable, so that if you ever go to execute that address, a page fault happens. Same, if it's read-only and you go to write to it, a page fault will happen as well. This can be used for the kernel or the hypervisor to protect memory from being modified by userland code, for example. There's also executable only, but that doesn't exist on x86 processors, but it does exist on some other architectures. These bits of metadata and that is going to differ per CPU architecture, like x86, ARM, RISC-V, all that type of thing. You won't really know about it unless you look up the manual and refer to that for the CPU architecture you're analyzing. And all the protections apply per page. And a page, when we talk about a page, we're talking about the lowest, or rather, a page is a slice of memory, so to speak, with the page size typically being the smallest, or rather just the size of a single allocation that a CPU can do. So for example, on x86, there's 3 page sizes, 4 kilobytes, 1 megabyte, and 1 gigabyte. Some architectures have different page sizes. So, ARM will have different set of page sizes that it can support, which may overlap with x86, but may also differ. Windows primarily configures the CPU to use 4 kilobyte page sizes for the most part. You can mix and match on some architectures. But what this means is, since the lowest page size is a 4 kilobyte, is 4 kilobytes, if I actually go to allocate less than 4 kilobytes, say I go to allocate 2 kilobytes of memory, what actually happens is that if I request 2 kilobytes of memory from the operating system, it can only allocate minimum 4 kilobytes. It can't do any smaller than the lowest page size offered by the CPU. So what typically happens is it might allocate 4 kilobytes, but then it might give me a pointer to maybe an offset into the page where there's only 2 kilobytes remaining, or it might give me a pointer to the start of the page and say there's 2 kilobytes there, but really there's more. It can handle it in different ways. But this is also important to note because page table protections apply per page size. So let's try to visualize this for a second. If a page size, the smallest allocation that I can do is 4 kilobytes. So this is my page. Say I allocate 2 kilobytes of data, right? I want to get 2 kilobytes from the operating system, and say that this is my 2 kilobyte chunk. And then the bottom part is just the remaining leftover bits of that 4 kilobyte page. Now, if I'm in this 2 kilobyte chunk and I actually do some sort of overwrite, well, actually, say I want to make this 2 kilobyte chunk read only, right? The page protection actually applies, first of all, to the whole page. So if I want to make this 2 kilobyte chunk read only, I have to make the entire 4 kilobytes read only. Likewise, if I wanted a 2 kilobyte chunk here to be read only, but then consequently, I also wanted this 2 kilobyte chunk to be read write, I wouldn't be able to do that in the one 4 kilobyte allocation. I'd have to allocate a separate page that's that's obviously has to be 4 kilobytes minimum, and that separate page would have to be marked as read write. That's the only way you can have different permissions. It's per page. What this also means is if I make the 2 kilobyte chunk here a pointer, and say I want to detect when an overflow, say this one's writable, say read write. Okay. And say, I've got a pointer in my program. It points to my 2 kilobyte chunk. Now, say this pointer, I allocated 2 kilobytes of memory, but of course, since it's got allocated to a new page, there's actually 4 kilobytes here, and it's placed at the start of the 4 kilobyte page. But say I overwrite this pointer through a buffer overflow or something, and it actually ends up writing to, past the 2 kilobyte chunk down here into the 3 kilobyte or 4 kilobyte region. First of all, if this page is marked as read write, which it would be to support this 2 kilobyte chunk read write, I'll just be overwriting more writable memory, and there wouldn't be a page fault or any immediate bugs that would come out of this. But clearly I'm doing something wrong, right? I'm overflowing a buffer, but the CPU just sees that I'm writing memory into a location that's writable. So the CPU is not going to know that I'm doing something bad. It just sees that I'm writing into memory that is marked as writable. So to kind of detect these things, this is where guard pages come in. This is more of a thing to enhance your fuzzing, where you enable page heap and things like that. But it helps understanding the operation of MMUs and allocations and things like that, which helps with reverse engineering as well. So what happens there instead is you can actually allocate this 2 kilobyte chunk towards the end of a page. And because this 2 kilobyte chunk is at the end of the page, now if you go into overflow past 2 kilobytes, you'll actually be running into overflowing perhaps a new page. Right? Because it's at the end of the 4 kilobyte page, any overwrites will go to a different page entirely. And then that different page can be marked no access. So any reads or any writes to it will cause a page fault. And these are kind of how guard pages work, where your memory allocations are allocated at the end of a page. So if I allocate 2 kilobytes of memory, that 2 kilobytes of memory is going to be in the last remaining 2 kilobytes of an existing page, such that when you overflow it, the address that it's going to overflow to next is going to be mapped into a no access page. And the CPU will detect that you're trying to read or write or execute no access memory, and it'll raise a page fault, and that can be detected. This also means if you're using like the Virtual Protect APIs on Windows to modify the permissions of memory, that's going to apply per page. So if I try to make a piece of memory, for example, so say I'm trying to make one address read only, and this address is 100 bytes. And then I try to make another address that lives in the same page to be read write, and this one's like, I don't know, 300 bytes. Then the read write permission change is going to overwrite the read only one. So if I do something like virtual protect, blah 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 address and set read only, this is just pseudocode, and then I do virtual protect, maybe address plus 0x100, set read write. If I did something like this, where I set an address to read only, and then I set 100 bytes or 0x100 bytes into that address as set read write, if that doesn't actually cross a page boundary and both addresses live in the same page of memory that's been allocated, then the set read write virtual protect will overwrite the set read only virtual protect, because if they're both applying to the entire page. And on Windows that's commonly a 4 kilobyte page, but it can also be a 2 megabyte page or even a 1 gigabyte page, which is a lot of data, right? So it's key to remember that all these things that operate with memory, virtual protect and things like that, typically they're going to operate on pages. And so it's key to know what the page size is and what if the addresses you're addressing live in different pages or if they're actually the same page, and if there's any other data shared on that page with the data you're trying to protect, things like that. There's also special addresses that map to hardware. This is what we call memory mapped I/O. And this is because we have other hardware on our systems, right? We have graphics cards, we have network cards, we have serial ports, VGA, things like that. And the way we can interact with them, if they support it, is via memory mapped I/O. This means that certain memory addresses won't actually go to memory. They'll go to hardware. So for example, the memory address EFFEC000 is actually, I believe this is the memory address associated with the serial, with the virtual serial device for Hyper-V virtual machines, which means that if a guest VM goes to read or write to that memory address of EFFEC000, it's not actually going to go to RAM. It's going to go to the serial device. And likewise on hardware and that, the address B8000 is actually the address of x86 VGA, which means if you go to write to that address or offsets to that address, you could actually be talking to the VGA controller or something like that instead of actual memory. Sometimes these are rather static addresses. Sometimes they're dynamic and can be passed via the ACPI tables. This is more of a thing that bootloaders and things like that will be responsible for. But the key thing to know is that they exist. Memory mapped I/O exists such that when you go to talk to a specific address, it may not actually go to RAM. So if you're looking at code and you see that code reference an address that's like 0x, B8000, and say, it writes to that address, a buffer of 8 bytes. So say you see somewhere in code that it's doing a 8-byte write to this B8000 address. Now, this address, if this is the actual physical address that it's going to be writing to, on x86 systems, that's going to go to the VGA controller. That's not going to go to RAM or in memory. The CPU is going to see this address and it's going to know that it corresponds to hardware, and it's going to pass through this write to the actual hardware, right? In this case, it's VGA. It could be your graphics card, it could be your network card, it could be things like that. So it's key to note that when you see a write to an address, it could be a memory address, it could be hardware. That's going to depend on what you're reversing as well. If you're reversing an operating system or a bootloader, you'll see this a lot more than you would if you're just reversing some userland binary. Next up, we have x86 and x86 general information, theory. We'll be looking at the registers, specifics to x86, and a lot of the common instructions that we will encounter when reverse engineering x86 and x86-64 code.